Happy Thursday. We're almost done with techniques of integration. We have tonight, then we have Tuesday night. All of the antiderivatives that we've been looking at so far, and every function has had an antiderivative. Generally speaking, this is not always the case. In fact, 95% of the functions do not have an antiderivative. The vast majority of them don't have antiderivatives. For example, something like e to the negative x squared. That has no antiderivative. However, it still has an area under the curve. So the question is, how can we calculate integrals of functions that have no elementary antiderivative? Oh, we have to do it numerically. All right, so this gives us an approximation. As with any approximation, any numerical technique, there is always an error associated with it. There are three numerical techniques that we study: midpoint rule, trapezoidal rule, and Simpson's rule. Simpson's is the favorite of the three.
Oh, I know, but they kind of the
There are two other methods that you have studied. You should have studied. The right endpoint and the left endpoint. Right endpoint, left endpoint, and midpoint should sound familiar. Right. Those are the three types of Riemann sums studied in Calc 1. Well, they're also numerical approximations. So the two new ones are going to be trap rule and Simpson's rule. If I can remember the rules. One and was it one? I'm gonna look it up. I don't remember off the top of my head. So this is the formula for midpoint rule. N is the number of subdivisions of your interval of integration. Right, and then delta x is defined to be b minus a over n. As a refresher, right endpoint approximation was what? Delta x and summation I equals 1 to n. I think it was what, f of x sub I, which we can replace as what it was, a plus I delta x. The left endpoint approximation delta x summation I equals 0 to n minus 1. F of a plus I delta x. But so again, these are technically valid numerical techniques for approximating an integral. Right, so those are the old ones. New ones. Trapezoidal rule. T sub n. 1/2 delta x. Summation I equals 1. Now. Y0 plus 2y1 plus 2y2, so on and so forth. Y sub I is defined as f of x sub I. Which is just f of a plus I delta x. This can be rewritten. Obviously, y0 is going to be f of a, right? Yn will be f of b, so those are the two endpoints. Notice that all of your middle terms are being multiplied by 2, so that's where we can just simplify it using a summation. That form is going to be important when we go to code. Okay, seriously, I know. Already there. Yep. Again, n is the number of subintervals. Delta x is b minus a over n. And finally, we have Simpson's rule.
Combination of them, right?
This is Simpson's rule. And again, y sub I is f of x sub I, which would just be f of a plus I times delta x. There's one additional stipulation. For Simpson's rule, go away. Your number of subintervals, your number of divisions must be even. Right, so you can't calculate, for instance, S sub 3.
So what shape is Simpson rule representing? Like visually, what would you be taking the area of?
It's still a curve.
Well,
It's just
yeah,
how you divide it.
but previously we were doing like either into rectangles or into trapezoids. So what shapes are these?
Polygons. Parabolas, I think they are. Yeah, parabolas. So take the line segments of the trap rule and replace them with parabolas instead. That's Simpson's rule. This can also be rewritten, albeit a little bit trickier to do. So the 1/3 delta x. Right. Y naught will be f of a, yn will be f of b. Notice that all of the odd indexed y's are multiplied by 4. The what, n minus 1, I believe. Check. No. Code. What did I do? I see what I did. Yeah, it's going to be a bit of a pain to actually write out without the code, so I'm probably just going to leave it like that. Obviously, the larger the number of subintervals you use, the more accurate the approximation gets. Bless you, right? So here's the problem with numerical techniques. All of these are known as, no, this isn't really iteration, is it? It's sort of like iteration in that if you want it to be accurate within a certain number of decimal places, you're going to have to calculate. So for instance, SN, you're going to have to calculate S2, then S4, then S6, then S8, right? And you keep going until your last two agree to whatever those decimal places are. So if it's 5, you keep going until your answers agree up to 5 decimal places. You have no idea how long that's going to take until you actually start doing it. The ones we're going to look at. Oh, yeah. Simpson's rule generally is pretty quick, so that's nice. But trap rule and midpoint rule are not. As we're going to see in the examples I have. So that's a bit of a problem. You don't want to be sitting there and doing 100 of these by hand. You're going to be there all day. This is where technology comes in. So we will be using Mathematica to write code. Luckily, 2 of you are already familiar with this because we did this in Calc 1 with Newton's method. So what we're going to do is going to evaluate the integral from 0 to pi over 4 of x times sine cubed of tangent of x, accurate to 4 decimal places using the 3 methods: trap, midpoint, and Simpson's. Let's start with trapezoid rule. This is actually not mandatory, but it is going to make things a lot easier. First, define your function. So the function is what you're integrating. It was what? It was x times the sine of the tangent of x all cubed, right? The semicolons are also optional for this stage. Because if you just hit enter, it's going to go down to the next line. I'm going to set a to be the lower limit of integration, which is 0. Set b to be the upper limit, pi over 4. I'm going to define a function delta x and define this as a function of n. And it's just b minus a over n. Actually, I'm just going to get rid of that semicolon. I don't need it. I'm going to create a variable known as accuracy. We set this to our desired accuracy. We wanted, what, 4 decimal places? So set it to 10 to the minus 4. I'm going to define I to be 1. And another new variable, error. I'm also going to define that to start out as 1. I need t sub 1 for my code, even though you would never normally calculate it because it tells you nothing. I just plug it right into the trapezoid formula with n equal to 1. So that's how I'm defining t1. So it's going to be some value. That's all the preliminary stuff. Now for the actual code. I'm going to use a while loop. While our absolute value of our error term is greater than or equal to our accuracy. Right, so that is the test of the while loop. If it passes that test, it continues the loop. Just put greater and then an equal sign after that, and it'll automatically convert it to that. So this is, again, purely optional. You can just write it out, keep writing. Aesthetically, I'd prefer to have separate lines, just so it makes it easier to read. So that's why I'm doing an enter. Now for the actual body of the loop itself. We want to calculate the next term, the next trapezoid term, right? So we're going to want to calculate T2, then T3, T4, right? So on and so forth. So I'm going to say Ti plus 1 is equal to 1/2 delta x of I plus 1 times f of a times f of b, right? So that takes care of the two end terms. Now we just need the middle terms. Remember, we said that was 2 times the sum. Right, so what are we summing? F of a plus j times delta x I plus 1. And so that's the term of the summation. Now I just need to tell it what is the summation index. In our case, it's j, right? Where does it start? 1. And where is it going to end? At I. Because it's I plus 1 minus 1, right? 1 less than the number of subintervals. Those are curly braces, yes. Oops, I don't want a comma. Semicolon. So it's going to calculate the next t. Then what I want it to do is calculate the error. Well, it's going to be the term we just calculated minus the previous term. Right now, what I could do is instead of up here, instead of having absolute of error, I can just do error and make this an absolute value here. Same thing, doesn't matter. Then I'm going to tell it to add 1 to I. Right. So I starts off at 1. We defined error to be 1, which is clearly greater than or equal to 10 to the minus 4. So it's going to go to t of 1 plus 1, which is t2. It'll calculate that. It'll calculate the error of t2 minus t1. It'll then add 1 to I. So now it's going to be I equals 2. Then it goes to the test. Is that new error greater than or equal to 10 to the minus 4? If it is, it will now calculate t2 plus 1, t3. Set the error as t3 minus t2, add 1 to I, go back up, run the test, right? And it'll keep doing this until the test fails, at which point it then kicks us out of the loop. I'm now going to go ahead and have it print out the latest t term. Anything you put inside quotations, it's going to print out as text. think that will get me what I want. Right, the reason I'm using I is because remember it's adding 1 to I before it runs the test. Right, so if the last one it calculates before kicking out of the while loop is T5, right, that's I equals 4, 4 plus 1, and then adds 1 to 4, which is 5, so this should print out T5. Moment of truth. Shift, enter. No. Okay. So what did I do wrong?
This is supposed to be capitalized.
No, I'm defining it as lowercase. Cubed, yes. 0 to pi over 4. Delta xn is b minus a over n. Yes, actually 10 to the minus 4. That's what's one error starts at 1. T1 is delta x 1 plus f of b. Right. 1/2 f of a plus f of b plus. Oh. That should have been a plus, not a times. Yeah, that would change everything. I had f of b and then I did times 2 when it should have been plus 2. Perfect. To get the desired accuracy, it took 15 subintervals. Whenever you only want to go up to 4 decimal places, that's giving us more than 4. So we just say 4 right here. So 0.0716. Another thing we can do is now that we know that there's not a leading term, I can actually come back up into my code and say I only want 4 terms in the numerical approximation. Why is it going out that far? It's counting sig figs, isn't it? So I don't want 3, I want 4. Or I don't want 4, I want 3. There we go. Right, because it's 3 sig figs. Now again, problem with that is you don't know what it's gonna, how many sig figs you're gonna need until you actually run the code and see what it spits out. Right. So there would be our trapezoid rule. So what I'm going to do is just do this. Copy and paste. Great. Paste that as a picture. No, you won't let me? Okay. Why did you all highlight? Actually do a screenshot. Why are you not working with me? Now midpoint rule. All of this is going to stay the same. So why not just copy and paste it? Right now, if you want to, what you can do is you can insert text, right? Comments. I could do this. Right, just to separate the code. It reads this as just a comment, not as actual part of code. Like with trap rule, I'm going to need M1 for my code. Let's go ahead and define M1. Delta X of 1 times, it'll be what? F of A plus 1 minus a half. Oh, I put that in parentheses originally. Okay, that's fine. All time, so that's all times delta X of 1. It's going to be another while loop. In fact, most of the body is going to be the same. The only thing that's going to change is instead of T, right, we're calculating M. Formula for M was what? It's delta X times sum of what was it? It was F of A plus 1 minus a half. Wait a minute. 1 minus a half times J, right? So J over 2. That's it. Or do I have a different code here? Uh-oh. No, it's not J over 2. It is a half. It's J minus a half. Yes, it is. And it's F of A plus the quantity J minus a half times our delta X. And J goes from what? 1. The I plus 1 minus 1 again. Or no, it goes all the way up to N, right? So I plus 1. All right, now all we have to do is change these T's to M's. and change these T's to M's. Of course, the moment of truth. Did I do it right? I did. Now shift enter, and there is M accurate to 4 decimal places. This one only took 12 iterations to get to the desired accuracy. And 12 subintervals. So it's definitely a bit more efficient than trap. I'll just go ahead and paste that over. Simpson's rule. Again, all of that is going to stay the same. So let's just copy and paste. Now remember with Simpson's rule, N has to be even. So we're not calculating S1 first, we're calculating S2. That's 1/3 times delta X of 2 times, we want f of A plus f of B, those are the two endpoints. And then we have 4 times y sub 1, right? So that will be f of A plus delta X of 2. The test is going to stay the same for the while loop. Only the first line of our body that's going to change. This is where it's going to get a little tricky. Remember, S has to, N has to be even for Simpson's rule. I can't just do I plus 1.
I plus 2.
1 plus 2 is 3.
I said I plus 2.
Right. I starts off at 1.
Oh.
I could go back and change I to start at 2. If I do that, then I can't follow the code I already have written. I don't want to confuse myself any more than I already did when I wrote this code. 2 times I plus 1. Right. So this will give us S4, which is the next in the line. We already know 1/3. delta x will be delta x of, same thing, 2 times I plus 1. F of A plus F of B will stay. This is where we have to get clever. All of the odd indices are being multiplied by 4. So let's look at those first. 4 times some summation. Definitely going to be of F. It'll be A plus J times delta X of the same thing. That should be good. Our index is J. One's odd one, so we're going to start at 1. Oh, okay, yeah, I was looking at the wrong one on my code. Yep. Start at 1. We want to go to the one just before the final, right? We want to go the n minus 1, where n is even. Well, our n is what? It's 2 times I plus 1, right? So 2 times I plus 1 minus 1. Here's the thing, though. The sum is going to run j equals 1 through whatever that term is. That includes all the evens. Right, so it'll be 1, 2, 3, 4, 5. We don't want those, right? We just want 1, 3, 5, 7, 9. What this extra bit here says is each term of the sum, how do you want to increase j? So I'm saying j is increasing by 2 each time, not 1. Right, so it'll go 1, then 1 plus 2, right, then 1 plus 4. So it's going to give me all of the odds. There's that sum. So that takes care of all the odd indexed terms. Now we need the even indexed. Those are all multiplied by a 2, aren't they? So plus 2 times, same sum. J now starts at 2. And it goes up to n minus 2. And so 2 times I plus 1 minus 2. This again gives us the same problem though. It'll run J 2, 3, 4, 5, 6, 7, 8, 9, so on and so forth. So again, we need to tell it that we want J to increase by 2 for each term of the sum. That should be the S's. The error is also going to have to change a little bit. All right, so it's going to be the term we just calculated minus the previous term. The S of 2i. And I still want I to increase by 1. So this is going to be S. I want 2i, right? Not I. So this will be S of 2i. That should get us what we want. Ha! Yes, victory is mine. 0.0710. Notice S only required 6 subintervals. So if you're calculating by hand, that would only have required 3 calculations, right? S2, S4, and S6. Midpoint required 12 subintervals, trap required 15. So yes, S is way more efficient. However, writing its code out was more of a pain. I won't lie, when I first wrote this code, I think it took me several hours. Trap was fine, midpoint was fine, I got those fine. I was trying to figure out how to write out S with N only being even. That took me a bit.
These are one other problem, correct?
What makes Mathematica the best place to do this on?
It's on, it's just the only language I know. Python would be better, but I don't know Python. Plus, Mathematica is free to our own students. I think Python might be, but I'm not 100% sure.
It is.
Python would probably be more efficient. It's a more efficient language. right? Of course, right, because you can use this for any problem, I'm not posting this file anywhere. Otherwise, you'd just be able to open the file and make the appropriate edits, and it wouldn't be much of a test. We're going to integrate 1 to 2 x cubed times the square root of x to the 5th plus 2x squared minus 1, accurate to 6 decimal places using the 3 rules. And now, for the reason I took that time to write out those preliminary steps, I don't have to recode anything. All I have to do is come back and just make the appropriate changes to the functions, the a, the b, and the accuracy. Everything else will stay exactly the same. New function, x cubed times the square root, x to the 5th, plus 2x squared plus 1. A is now 1, B is 2, and error, we want 6 decimal places, so we want 10 to the minus 6. I am going to make one slight change. I'm going to get rid of that 3 sig figs in the numerical approximation, because new problem, we don't know what we're looking at. Have a little bit of fun. How many subintervals do you think we're going to need? Yeah. I just deleted the comma 3.
Oh.
How many subintervals do you think it's going to take to get the desired accuracy?
Was that really +1 in the original problem? I feel like it was a minus. Maybe I saw it wrong.
No, it is minus. I saw it wrong. That's an easy fix. What do we think? How many subintervals? So last one required 15. And that was 4 decimal places. What do we want to think for 6? Of course, granted, it is a different problem. Oh, nobody even wants to take a guess. That makes me sad. And no cheating in running it before taking a guess. 20. Higher. Higher. Higher.
45.
Higher. What is it? That's definitely lower. 500 lower.
200.
100 lower.
75.
Higher. Higher than both. Slightly higher.
97.
was gonna take a while because of how many it is. Uh-oh, that's not right. Should be 97. Oh, crap. What the hell happened? Oh my god. I read it wrong. It's not x cubed times square root. It's x times cube root. Yeah, that's going to make a difference. Perfect. $97 subintervals required. Now, if that was the original problem, 275 subintervals required. Do you really want to sit there and calculate 275 of the bloody things by hand? Ah. This is why we invented the computer. All right, so midpoint. One. Those. Again, I'm just going to remove this comma 3. What do we think here? So what was it? Last time we went from 15 to 12. How many subintervals is midpoint going to take here? What was it? Slightly higher.
75.
Higher. Higher. 77. Simpson's rule. I'm again going to get rid of that 3. I forgot to check. These are only 4 decimal places, by the way. That one's 5. So we're going to need 7 sig figs to get 6 decimals. Just still a quick fix. Which means here I'm also going to want 7. How many do we think for Simpsons? 20? Lower. Remember, Simpsons, you have to have even.
10.
Lower than 16, higher than 10. 14. Went from 97 to 77 to 14. This is why Simpson's rule is preferred. At least that's bearable. You only have to do 7 of them.
That's 7.
No, sig figs. Right, so that 3 is significant, right? That's why you can't just go right off the bat, I want 6 decimal places, I'm gonna do comma 6. Because you don't know how many sig figs are gonna be before. Like the previous one, the first 2 digits were not significant, right? So we want 4, so I needed to put 3 sig figs. First, we're going to plot the curve 1 over square root of 2 pi times e to the negative x squared over 2. We're going to look at it over the interval minus 3.5 to 3.5. This curve is the standard normal curve. If you studied statistics, you know how important that curve is. We will then go ahead and evaluate the integral from -1 to +1 of f of x, accurate to 4 decimal places, using the 3 rules. That's e to the minus x squared over 2. What we're actually doing by calculating this integral is we're actually calculating the percentage of data that fall between 1 standard deviation away from the mean and a standard normal. Again, if you've studied statistics, you should have a good idea of what we should wind up with. So let's start with trap. Change this. 1 over the square root of 2 times pi times e to the minus x squared over 2. -1 to +1. That goes back to 4. And then before I actually run this, let's go ahead and plot it. Right, so there's the standard normal. Oh, that's definitely not what I wanted. Okay. Oh, I wonder if that's why. Yes, that was why. Okay. So that's the area we're finding with this integral. I don't care if the ticks don't show up. That's fine. Now let's run up and redo this. So again, I'm going to get rid of that 7. And we don't know how many sig figs we're going to have. Took 16 subintervals. So it looks like we're going to need 4 sig figs. 0.6821. Again, 4. All right, midpoint. Ours 13, get 0.6832. Simpsons requires 8 subintervals. 0.6827. Because it told us accurate to 4 decimal places. Right, so 10 to the minus 4. Right, so by Simpson's rule, to 4 decimal places, about 68.27% of data will fall between 1 standard deviation of the mean. What about this? Within 2 standard deviations of the mean. Do you happen to remember what that is from stat? I don't think it's 0.84. I think I'm remembering.
95%.
95 what? I think it should be 0.95. Let's find out. So I'm just going to use Simpson's rule for this. So I'm just going to change A to -2, B to 2. Let's see what it gives us. And I think the rule is 95% from stat. And then there was also a rule for within 3 standard deviations.
99%.
It's about 99%. All right, let's verify that. A thing more specifically said 99.75%. Yes.
We have to, when we like have a problem like this, or whatever, do we have all like the filling, like the shading for the graph?
Not yet. We're going to cover that more when we look at applications next. And then the problem will specify if I want you to include a plot of the region, right? That would mean, yes, I'd want this, right? But again, when we cover applications, we're going to really delve into that. Are there any questions on numerical, the three numerical techniques? Let's see if I can. Let's... Don't remember where they moved it to. It's an old-fashioned way. So let's look at doing 1 or 2 by hand. Because you're going to have to do this for the quiz. For the test, if I ask it, it will require you to code, which means I will require a screenshot of your code. And we'll discuss that when the test is handed out. So we want to approximate the integral 0 to 1 sine squared of pi x dx using midpoint rule with 3 subintervals. Delta x. B minus a over n, right? So it's 1/3. X1. Wind up being 0 plus 1/3. I'm sorry, not 0 plus 1/3. It's the midpoint. So it's what it is. A plus 1 minus a half times delta x. That's 1/6. Why don't we just add 1/3 to a sixth? And that's our next test point. That's what? A half? And then the final point, x3 would be 1/2 plus a third, right? A half plus delta x. So that's what? 3, 2, so 5/6. That is the formula for finding the midpoint. It's a plus I minus a half times delta x. In this case, I is 1, so that's why it's 1 minus a half. Right? I don't have to worry about doing that for x2 and x3 because if I just add delta x to the first midpoint, I get the second midpoint, right? Because the interval length is delta x. But this would be 0 plus 2 minus a half times a third. Right? So those are the 3 points that we need. M3, delta x times f of x sub 1 plus f of x sub 2 plus f of x sub 3. Thankfully, these are nice values. What's sine of pi over 6? That's sine of pi over 3. It's a half. Squared is a quarter. What's sine of pi over 2? Squared is 1. What's sine of 5 pi over 6? Uh-oh. Still a half. Squared is a quarter. M3 is a half. Right now, this worked nicely because it was nice values, right? Otherwise, I'd be plugging this into a calculator to try and figure out the values. Give you time to work on this. You are allowed to use your calculator to get values. You just can't actually write a code on mathematical.